Our next speaker is a long-time NYR speaker. There is so much I could say about him. I think we all know all about him. I could praise him, I could laud him. But since he's coming on stage next, and I've praised him and lauded him so many times, I'm just going to say we're all very excited and very fortunate to have, yet again, for the 5th time at this conference, Dr. Andrew Gelman. Well, his music will be playing in a second. Hopefully.
Well, should I start while we're waiting for that?
All right, well, we might just have to introduce him without a song. I apologize, we're not getting his walk-on music. Too much going on my computer. I apologize, no walk-on music, but I'll just push him on the stage.
We don't passively perceive the world, we actively generate it.
There you go.
So perception, figuring out what's there, has to be a process of...
Can people hear me now? Oh, like you're turned off that goofy other thing. Okay, that previous talk was so inspiring. I think the things that people can do now that we hadn't even thought about before. I was talking with someone the other day. I felt that around the year 2010 was peak Bayes. Because that was by then we were able to fit a lot of models and understand what we were doing, but that was before all this deep learning stuff came that is so powerful and now is the most popular thing. Of course, there's room for different methods out there, but I just want to I really appreciate the kind of work that everybody's doing, that the kind of the hive mind out there. In Stan, we use AutoDiff. It was good to hear about AutoDiff. And I heard about Bob Carpenter, and I heard about automatic differentiation from a blog comment that I blogged on something related, and a commenter talked about it. And it was kind of counterintuitive. It seems like you can do derivatives using the formula, but you could do them. You can always do numerical derivatives. Why would you want to do AutoDiff? It seems like if you have a 100-dimensional function, then you can compute the numerical derivative by just evaluating the function 101 times and then subtracting. So people said, well, AutoDiff is faster, and it was hard to imagine how something could be faster than the dimensionality of the problem itself. But actually, when you have functions like exponentials, the computations are such that you don't have to repeat the hard computations in each dimension. That was just kind of an amazing insight. One of these things that once you realize, it changes how you think about things. And that was from a commenter, and then it got incorporated into so many other things. Now, regarding deep learning, a few years ago, I was at a conference at Columbia, and it was all about our big data stuff. We're trying to impress people. So somebody came up and said, I work in biology, and in biology we have megabytes, gigabytes of data. And then someone came up and said, well, I'm from astronomy, and in astronomy we have petabytes of data. And then the next person came up and they had some connection with the intelligence community and images, and they had whatever comes after that, exabytes or Googles of data. And then I got up and I said, well, I'm in political science, so we have megabytes of questions, but we only have about 20 data points. And so we actually have to do a lot of modeling because that's the only way to go about it. Recently, we've been thinking a lot about forecasting the upcoming presidential election, and there just haven't been that many presidential elections. Sometimes we have questions about 95% intervals. It's not even clear what a 95% interval means, in the sense that would mean you're wrong every 20 cases, which would mean in every 80 years, you'd be off once. So what does it mean to talk about, I'm not even going to have an 80-year career, right? So what does it mean to talk about intervals? They're supposed to be off once every 80 years. Well, when they talk about the 100-year floods, then you can say, well, here's a 100-year flood. It's supposed to happen only one every 100 years, but we have smaller floods, so we can scale that up. So maybe one way that we can understand 90% intervals or 95% intervals is by thinking about 50% intervals. It's challenging though. So what I want to talk about today is the gap between what we're doing and what we think we're doing. And also the gap between what we think we're doing and what we want to be doing. So this is the R conference, and R is, what is R as a programming environment? It's supposed to bridge that gap to some extent, right? R is not supposed to be the fastest thing. R is supposed to be the thing that matches your programming closest to what you would do as a data analyst. Now, nowadays, you could say, I mean, I've certainly heard people say, I hate R, but I use it because that's what everybody else uses. But that's not fundamentally what makes R R. R originally was not what everybody else used, or its predecessor S was not originally what everybody else used. R gained popularity for legitimate reasons. And the popularity, so if we're going to be at an R conference, let's think hard about this gap and what that gap means. So let me start with a story. So a few months ago, the country was being racked by a novel virus, which I guess I heard from the government that it's pretty much been resolved a few months ago. But as of March, it was considered to be a major concern. I think that was before they reopened the churches for Easter and all the stuff that happened since then. We were very worried, and I got a call from somebody I knew, and he said he knew this guy. He's a doctor, and he's trying some treatment for coronavirus patients, and they want to do a clinical trial. And it's one of these drugs that already exists, is being used to treat malaria patients. The way it works is you can treat them off-label, so you can just try it out right away. You don't have to worry about phase 1, phase 2, phase 3, all that. They want to design the experiment. And this was in the early stages when there were like hospitals in New Jersey were just full of people who were dying of the stuff, right? And so I talked to the guy, the doctor. He said, "Yeah, we are expecting the effect of the drug to reduce the death rate by 25 percentage points." It's like, not like, so the 25 percentage points, that's a lot. And he said, well, yeah, some people did a study saying it would reduce death rates by 50 percentage points, but I think that's a bit optimistic. So I'm just saying 25%. So how big a sample size do we need? So you can do the computation, you get about 126 patients, so like half in each group. And then I apologize, because I'm going to tell you something which we call a Findman story, which is a story that you tell that makes you look good and other people look bad. And I shouldn't do that. And I think if it were a little more artful, I would have changed the roles around so I was the fool and somebody else. Next time I tell it, I'll work on that. So forgive me, I'm going to actually tell how it happened. But sorry. So I asked him, I said, do you think, what if the effect is less than 25 percentage points? Like, what if it's only 10 percentage points? Well, then you need like 1,000 people in your study, right? So maybe you should do that. Like, there's a lot of patients coming through, and it's like, how small an effect could matter? Like, if the effect is 1 percentage point, I mean, sure, it's great to save a life now and then, but it wouldn't be so newsworthy. We're trying all sorts of things. But 10 percentage points, that's still newsworthy. That's still important, right? He said, yeah, that would be still worth it. But he thought the effect was 25 percentage points. Well, obviously, it has to be contingent, right? Like, the effect can't be 25 percentage points unless the actual death rate is at least 25% in the control group, right? So we're talking about this particular acute setting. How large could it be? So he said, no, I think it's just really, the drug does a lot. So then I said, but the drug might not work, right? So, yeah, of course it might not work. I can be wrong. That's why we're doing this study in the first place. Right? He didn't delude himself that he was omniscient at all. So, but then if it could work, how are you so sure the effect is 25%? So this is like the tyranny of notation or something, right? What does it mean to say the effect is 25 percentage points? If it's life and death, what it means is that there's 25% of the people who would have died if you hadn't given them the treatment, but the treatment saves them. Or maybe there's 35% of the people like that, and then there's 10% who the treatment kills or whatever. But for simplicity, say it's okay. So the whole point of the treatment is you want, for the treatment to be effective, you want those people. So there's 2 kinds of people, or 3 kinds of people in the world, right? Or 4 kinds. There's people who would die under either treatment, the people who would live under either treatment, and the people who would die under one and live under another. Okay. But let's the people you want in your study are the ones who would die under the control and live in the treatment. And so what you're saying, if you think the treatment effect is 25 percentage points, is that you think that 25% of the people in your study are that kind of people. But once you accept that, well, it could be less, right? I mean, it just depends who's in the damn study. Like it must depend on how far the disease is advanced and so forth. So of course the effect could be 10 percentage points, if it could be 25 percentage points. But in this sense, getting back to the gap between what we're doing and the gap between what we think we're doing, is people are set up to think that they're trying to estimate a parameter. But what you're really doing is, what you're really trying to do is figure out who are the people in the study. So it's like a completely different question. So now, with that story as background, let me get back to the title of the talk, which is Truly Open Science. So open science is more than data sharing, replication, pre-registration, partial pooling, and version control. Those are all important parts of data science, open science. Obviously, data sharing is important, replication. Pre-registration is an important part of data science, having a record of what you've done. Partial pooling is an important part of data science, open science, because partial pooling is generalizing from what you've learned to what you're interested in, right? That's very important to be kind of upfront about what you're doing. And of course, without version control, we are truly nothing, right? But open science is more than that. And doing statistics right is more than swapping Bayesian methods for p-values, or for that matter, swapping deep learning and cross-validation for p-values. To resolve the larger problems of the push-a-button, take-a-pill model of science, engineering, and policy, we need to move toward collaboration between researchers, data analysts, and people who design studies and work with the people whose data are being collected. Now, often that means that it's like, it's often social engineering that's important, right? So often what that means is that the subject matter people have to think less like statisticians sometimes. So like the doctor's actually dealing with patients, he should be the one telling me that he's looking for the people who will get cured and the people who won't, right? Like he's doing the abstraction inappropriately, which means that we're not working well as a team, right? So doing this, having this kind of collaboration requires the ability to simulate, graph, and analyze data using flexible platforms such as Stan and R and all the other things out there. Now, simulation, I have a principle now that I should never do an experiment or gather data without simulating fake data first. And I can tell you a story of where this happened to me. So I was doing a study. Actually, I think I mentioned this in a R conference a few years ago, which was our study on political penumbras. So the idea is that you ask people questions like, how many gay people do you know? How many close friends do you know who have been unemployed in the past year? Different things like that. And then you learn about the size of a group, the penumbra of a group. So, okay, it's interesting to know that 4% of Americans are gay, but maybe it's even more interesting, or also interesting to know that more than 50% of Americans have a close friend or family member who's gay. I can't remember if it's 50%, but something like that. If a group has a large penumbra, then that would suggest that it could be politically influential. Other groups, such as we asked people, how many women do you know have had an abortion in the past 5 years? That is a very small penumbra, because people won't necessarily tell you if they've had an abortion. So it's the penumbra as a function not only of the size of a group and who people know, but also of who tells people about these facts. But we did a study, a survey, which we asked people, we asked people how many people did they know, how many close friends, close family members, and other people they knew in different groups. And then we also asked them some political attitudes. And you see some correlation unexpectedly. We did a follow-up survey a year later, and we wanted to see whether people who entered a penumbra were changing their political attitudes on average. Well, you know, there's a kind of causal story there. I don't want to push the causal story too hard because entering the penumbra is not an externally assigned treatment. It's something that happens to you. It's a survey response. But nonetheless, I won't get into it here, but there are reasons we believe that we had a certain amount of causal identification. We're interested in this story. So what I want to do is see if you enter, let's say, the gay penumbra, you now know a gay person you didn't before, are your attitudes on certain gay rights issues likely to change? And so you can do a regression. It's simple enough to do the analysis. There's a lot of different ways of doing analysis, different ways of adjusting for it, things and like forking paths. I won't get into that. But what I want to talk about is what I didn't do and what I should have done. What I should have done was simulate fake data and analyze the fake data before getting anywhere. And the reason why is when all is said and done, we did estimate effects, and they were kind of like roughly 2 standard errors away from 0. We have a certain amount of confidence that they would replicate in the new study, but the standard errors are quite large. So a typical estimate might be an effect size estimate of 0.1 with a standard error of 0.05. We have an uncomfortably large uncertainty. So we're estimating for many groups, not just gays and unemployed. We had 14 different groups. So let's break this down. How do you get an effect size of 1, so of 0.1? So you can get an effect size of 0.1 if you say that these were survey questions measured on a 1 to 5 scale. And if you, like, what kind of changes are we going to expect? Well, let's just say that if you do change, you might just change by 1 on a 1 to 5 scale. Like meeting a gay person is not going to move you from 1 to 5. Not likely, right? And for that matter, it could move you in the opposite direction, right? So a net movement wasn't going to be that much. Then the other part of this 1 to 5 scale is that most people aren't going to change their views, because people have views. They're mostly not going to change. Now, one way of seeing this is that our two waves of the survey were a year apart. How much change would you expect to see in 1 year? Well, I'm bringing up this gay rights, same-sex marriage issue, in part because that was one issue where there were big changes. So over a 20-year period, support for same-sex marriage went up from about 30% to 60%, an increase of about 1.5 percentage point per year. That's huge, right? But then if you think about it, 1.5%, we had 2,000 people in our survey, right? So like what's 1.5% of 2,000 people? That's 30 people, right? So we're getting into pretty small sample sizes. And then if you look at entering the penumbra, most people aren't going to enter the penumbra in any given year. Most people are either in the penumbra already or they're not in the penumbra and they're not about to enter, right? So if 10% of the people enter the penumbra, then you're talking about 200 people in your sample that you're comparing. And then you talk about an effect of the small, you talk about small effects and you'll get these large standard errors. So we did something which was pretty common, which was we did our analysis. We gathered our data in a kind of hopeful way, thinking we'll run our analysis and get something good. But then in retrospect, we really barely had enough data to find what we were trying to find. We should have realized that ahead of time. So again, this is the gap between what we're doing and what we think we're doing, right? So what we think we're doing is gathering data and getting a quantitative measure of the changes and blah, blah, blah. What we're actually doing is getting a noisy measure of blah, blah, blah. So there's a saying, so statistics is very much about communication in various ways, right? So one thing I say when I teach statistical communication is that everyone trained in statistics becomes a teacher. No, not necessarily like my job is teacher, like that's my job title, or Jared does a lot of teaching, but also if you work, I think this is true for all of you in the audience, that if you are the analytics person, you're not just sharing your results with people. You're spending a lot of time explaining not just your results, but your methods. You have to explain the methods to people, and you have to really be a teacher. This is, people keep always coming up to me and telling me this. So now, so communication is very important. Programming is a form of communication. You're communicating with the computer. It's said that your most important collaborator is you 6 months from now, and she doesn't answer emails. And so when you are like, when we're programming, you're not only communicating with the computer now, you're communicating with the future you. So right now, what was I doing right before, a few minutes before this talk? What I was doing was fitting a hierarchical model to some subset of these data that I was just telling you about to estimate over dispersion of the social networks. And I programmed up like 6 different models in Stan, like, because I wrote something and it was like going really slowly and it wasn't converging, and then I reparameterized it, and then that seemed to work and it gave results that made sense. I was about to plot the results, but then I realized certain data hadn't been combined, so I combined the data and reran it. Now the results don't look right to me. The over dispersion seemed too high for the name penumbras, because they should be close to independent, except for Maria and Jose, but the other names should be closer to independent, and they're not. Like, I'm doing everything wrong. I mean, I'm doing a master class in how not to program, right? Like I should be simulating fake data from my model, this time not to understand the power of my study, but because like if I'm getting computing results that don't make sense, you want to separate whether it's your model not fitting the data, or your program not converging, or there being a coding error. Like, it's very easy to do that by simulating fake data. I just still not in the habit of doing it. I'm barely in the habit of haranguing other people to do it. That's the first step in any workflow, is to harangue other people to do things, and then you start realizing you should do it yourself. And so I'm not there. And I'm trying to work on it. So in that sense, I'm trying to apply some of the principles of open science to what I'm doing. This relates to something. So when I was way back when, before I was a statistician or a statistics student, I was a physics student. I worked in physics labs. I wasn't very good at physics, so I didn't understand it very well. So I stopped doing it, but I was kind of good at experimental physics, because that involved a lot of data analysis, so that's sort of how I ended up doing what I'm doing. But one thing I remember is that I'd be making a lot of graphs, and I quickly learned that when I was making presentation graphs for others, it was helpful for me to have subtleties that I would have in my own graphs for myself. So like, as much as I would think, well, no, other people want a simple story, actually, for me, what other people wanted was a kind of rough story, right? They wanted me to like if my story were a voice, they would want it to be like Kathleen Turner, not Whitney Houston, right? Like, they'd want the kind of roughness to it. And so people liked a graph that showed aspects of the model that didn't fit. And it's kind of a cheap trick, but like they say, like, if you want to convince somebody of something, you tell them a lie and they catch you out on it, and then they're like, oh, okay, well, there he was lying, so I think he's telling the truth now. So similarly with data, like, we make a graph and we say, look, the model is not perfect, look at this, then maybe people are more likely to trust the parts that they do understand, which I do not think is a dirty trick. I mean, I think that this is the honest way to perceive. But my point is that presentation graphics were like, I wanted to apply the principles of statistical graphics. Conversely, I found very early on, and I always teach this, that if you're only making graphs for yourself, you should apply principles of presentation graphics. You should make the axes, label the axes, make things pretty, and make things clear, give good titles, because you are communicating to yourself also. I think if I wanted to give you one message that you could take home from this entire talk, I guess I buried it at like the 30-minute mark when nobody's paying attention anymore. So get off your email for a second, you get off Facebook and say, yeah, I know that was pretty horrible what politician X said about politician Y. That was scandalous. It's the scandal of the week. We'll take a break from that for a second because I'm telling you the most important thing. And this is in my books too, but I'm telling you now because you weren't paying attention. The most important thing is to put multiple graphs on a page. And so you can see more, right? Real estate, it's everything, right? And I learned that. So, but people don't always realize that because they think of, oh, that's for presentations. I'm just doing stuff. So this is the same thing about the principles of open science, like it's a fractal, right? You should be open science all the way through. So I should be doing replication and fake data even when I'm fitting every model I fit. I should build the scaffolding every time. I shouldn't just assume things are going to work. And I don't do that. I don't always do that myself. So we have a saying in open science that honesty and transparency are not enough. And that kind of means two things. I mean, honesty and transparency are important, but what we say this partly because, like, sometimes, like in the open science movement, people will say, oh, so-and-so, they're using questionable research practices, or they're p-hacking, whatever, they're doing this bad stuff. And people have this reaction like, no, I'm not doing this bad stuff. Like, I'm a good person. And so, like, for one thing, you shouldn't act like people are bad people just because they do bad science. I mean, Isaac Newton did some bad science too, you know, like that's just the way it is. Bad science is part of science, right? And even if everything you do is bad science, it doesn't mean you're a bad person. Like, I'm really bad at basketball, it doesn't mean I'm a bad person, right? Okay. And so, but then so part of it is it's just wrong to kind of accuse people of doing stuff that's like immoral, if just because they're doing stuff that's hurtful, right? But then the second thing is the flip side is that you can't let people off the hook, because then they're like, oh, I'm not immoral, I'm not a bad person, therefore I'm not doing bad science. Like, no, you can be a wonderful human being, and even not just a wonderful human being, you can do pre-registration and data sharing and GitHub and all that and still do bad science, right? Just like the econometricians, they all focus so much on identification. Then the trouble was that once people were doing identification, they didn't realize you could still do bad science. You do identification and bad science, right? Anything fits with bad science. That's fine. So we have to be aware of that. But if you think about these cases where what I'm calling science is superficially open but not truly open, is that people are not mapping this gap between what they're doing and what we think we're doing. Now, let me conclude, I guess I have like 5 minutes here, with an example. So it's a recent example, which is election forecasting. And the first time I ever did election forecasting was in 1992. The story actually starts 4 years before that. I'm a political scientist, and my Michael Dukakis' election victory party in 1988. Michael Dukakis he was the Democratic nominee for president in 1988, and so he did not actually win. So the tickets to his victory celebration are just a historical amusement. I didn't actually go to the party, but I had a colleague who political science professor who had these tickets. We did not, it was months before the election and Dukakis was comfortably ahead in the polls, and my colleague told me that that he showed me the tickets and said, he laughed and he said, Dukakis is going to lose. And I said, what do you mean? He said, well, I've read some books by political scientists and you can forecast the election based on the economy and presidential popularity and stuff like that, and it looks like a good year for the Republicans. And my colleague was right, so of course that had a big influence on me. We wrote some stuff about elections being predictable, so to do this we needed to make an election forecasting model. So I did that. We computed all sorts of fun pop probabilities. It was before the internet and all that, so somehow I couldn't get, people weren't really interested in all this forecasting stuff. Like, it was a very niche area. But in more recent years, election forecasting has become very popular. So things have changed. I don't quite know why. But my colleague, Elliot Morris, and my colleague at The Economist, and my student Merlin Heidemans and I have been working on, we constructed a model that we fit in Stan to forecast the 2020 presidential election. So we think that Joe Biden has like a 90% chance of winning. The model combines several pieces of information: state polls, national polls, as a model for non-sampling errors in polls. It has a fundamentals-based forecast, which it uses as a prior. It has previous election results in the states, and it has a kind of complicated, not that complicated, but it has a time series model for how the polls and public opinion change over time. And we do have it on GitHub. Probably the most open thing about it is that there were 3 of us working on it, so we kept trying to poke holes in it and find problems. And then we published it, and then after it was out, some people had some issues, and we looked carefully, and it turned out we had a bunch of coding errors and things where our program was not doing what we thought it was doing. And I think it is a weakness of a lot of statistical methods, including what we do. And I think it's a weakness of a lot of deep learning methods too, is that they don't really have this, like, future, weakness is good, it's like future research. They don't really have good ways of checking or understanding this gap between what you're doing and what you think you're doing. So there is some research on interpretable machine learning, but it's kind of like coming from the perspective of, yeah, you're doing the right thing and you just have to explain it to, like, the salespeople, right? And that's not really what I'm talking about. I'm really saying, like, understanding these gaps. And I've done some research on model checking, and Dave Bly at Columbia has done some research on posterior predictive checking too. But again, it's kind of, that's coming across as like, yeah, we know what we're doing, but it might not fit the data, so let's fix that. We're not really fully addressing that gap. It's something that we need to do. Currently, a lot of the gap is being addressed in the social arena, that our model is out there so people can criticize it. But to be honest, like, you put your code on GitHub and most people aren't going to look at your code. I mean, there's lots of errors. We had errors in our code that were sitting there for a month or 2 and nobody noticed at all. So you don't, like, people will work on easy problems for free, but it's sometimes harder to get them to work on hard problems. So my message to all of you to conclude is that you have to, that when we talk about tools such as R and Stan, these are expressive tools. They allow you to express yourself, to, like, move in ways that you could not easily move by yourself. And we gradually, think of yourself, think of you, whoever you are, how first you could do, like, you learned how to do simple things in the computer. At some point you learned regression and you didn't really understand it. Maybe you were doing stepwise regression or something. You develop certain, you learn things by, like, trying out, like, templates, like imitating somebody else's tools, and then gradually you got used to things. And how that went. And imagine yourself as, like, continuing to this. So we talk about the exploration-exploitation trade-off. Well, you should always be exploring. If you're 85 years old, you should be exploring, not optimizing. There's always room for exploration. People are always optimizing too soon. Okay? So you're going to be continuing to learn. How can you be a more effective colleague, teammate, and how can you more effectively help the world as a data analyst or as a programmer? Of course, the way that there's two ways. You get better at the things you already know how to do, and you learn new skills, right? And how do you do that? I think if you can focus on that gap, and I accept that this talk was more conceptual rather than like constructive, partly because I didn't really realize I was going to talk about this gap until like 5 minutes into the talk, so I didn't prepare this. But if you think about this, if you think about where this gap is and how you can build your own tools to solve that, I think you will become a better learner, and I think you'll be a better colleague and problem solver. So that's what I'd like to help you do that, and I feel like, and I think part of it, if you think that's like the third leg of the stool, because part of it is the ideas of open science and good practices, which R is like, you know, both good and bad in terms of has good and bad aspects of that. And then part of it are actual statistical or data analytic tools, tricks that you learn. But then this third part is being very self-aware of what you want, what's happening, what you're expecting to see. It's like applying ideas such as pre-registration and replication to your own learning process. So I think if you can introspect like that, you can become a more effective problem solver and a more effective teammate. So I hope that happens for all of you.
Okay, everyone. Normally, we have a no question thing at this conference. So that's why we keep it moving. But only 2 people have ever taken questions at this conference. Vivian Peng, the very first year, because she finished a little bit early, so I threw her back on stage, and Andrew has. So there was one question that came in earlier, and I'm sorry if this is a dousing flames on a fire, but we want your take on Nate Silver and 538 forecasting.
Oh, I wrote something on our blog today about that. So, yeah, I think, well, as I wrote there, I think what he's doing is very similar to what we do, because as there's a principle of Hal Stern, which is the most important thing about a statistical method is not what it does with the data, but what data it uses. So you have state polls, you have national polls, you have some fundamentals-based forecast, you have a model for how these things are changing, you have a model for polling error, and you put that together and you have idiosyncratic factors. So we tried to isolate it. How are they different? So I think his fundamentals-based forecast is different from ours. I think his is a little more informed by 2016, and for ours is kind of more influenced by like economic factors. So our fundamentals-based forecast would be Biden getting 54% of the two-party vote, and Nate's is more like 52%, which is what happened in 2016. I kind of like our poll aggregation approach better than his, partly because we're cheating. We're using Bayesian methods, and he's like trying to like come up with a bunch of clever ideas one after the other. So like I feel like he can't win that one because he's just trying desperately. At best, he'll reinvent Bayes' rule. I don't think that's really gonna work. He has like I don't quite know how he deals with non-sampling error. I like how we deal with that. It's hard to say because there's. I felt that looking at the percentage chance that someone wins it's hard to know what to do with that. Our 95% interval for Biden's fit share of the two-party vote is 50% to 54%. So like, 50% to 58%. So like, well, what if Biden got 49%? Like, would I be so surprised at the two-party vote? Well, like, I don't know. Like, you know, like, would I bet 95%? It's hard to answer these questions. Like, it seems like Biden could get 60% of the two-party vote. Like, it doesn't seem completely impossible that the Republicans could abandon Trump. On the other hand, they haven't abandoned him yet. Like, you can kind of go in circles about this, which I just think kind of demonstrates that the limitations of these forecasts. Like, ultimately, these forecasts, I'll take a kind of Tukey line on it and say these forecasts are products of data. I mean, they're human products. They're little bridges we're building. They're not truly the probability that someone would have. Like, would I bet on this in some way if I wanted to decide what to bet? I don't believe the betting markets, I think, undervalue Biden. I think the betting markets are too informed by 2016. There's a principle of Bill James, which is that the alternative to good statistics is not no statistics. The alternative to good statistics is bad statistics. He said that because of there would be sports writers who would say, hey, Bill James, stop doing all your fancy number crunching. I want to base things on more qualitative features. And Bill James pointed out that they were basing them on qualitative features, like somebody hit 350 in Fenway Park once and things like that. People were using the numbers. They just weren't thinking about them seriously. They were using the numbers as words, as he put it. So similarly, I feel, actually, people in the betting markets might feel like they're being super conservative by not favoring Biden too much. They might think that they're being really hard-headed. What I would say is they're partially pulling towards 2016, and maybe that's right. That's their decision. I don't know if there's something about that. Speaking externally, if I were not me and I were not Nate and I were just someone else coming at this from the outside, what would I say? I'd say, well, I think that economist model has some sophisticated poll averaging. I would guess that they do a pretty good job of combining the information efficiently from state and national polls. Point in our favor. Point number two is that there's 1 million polls. So that point in our favor is not such a big deal. We're making very efficient use of data that there's tons of. Nate's model, his model is different from ours. Well, gee, those economist people know a lot, but like Nate knows a lot too. Like, maybe split the difference. I'm not going to split the difference. I kind of like what we did, but if I weren't me, then I'd probably do that. You're silent, Jared. I can't hear you.
Should we be aggregating your two predictions?
Well, I wouldn't do that. But like, maybe you should. Like, it's like, it's hard to say. I mean, we're not. So people say, like, well, what if what if one of the candidates, they're old guys? What if they get a stroke and they're replaced by their running mates? Like, well, that would make a difference. That's not really in our model. Like, well, it's implicitly in the error term, but like, it's never happened before. But it could. Like, it is hard to draw the line. I mean, it's like there's two extremes. It's hard to be completely kind of objective and purely numbers based because we do care about the outcome, but at the same time, it's hard to give a total probability answer. Like, so I joked to the reporter at one point, like, well, this doesn't account for possible meteor strikes, right? Well, that's kind of silly, but like, as I said, I don't think there's a precise answer. I was getting on Nate's case a little because his 95% interval for Florida said that Biden was going to get somewhere between 43% and 59% of the vote in Florida. It's hard for me to picture Biden only getting 43% of the vote in Florida. Like, it seems so low, but like, I mean, that's the story is somehow the economy is booming back and people like that, or things are variable, or something happens in Florida, something says, there is variation from state to state. Part of the reason we have kind of narrower intervals is because in the era of political polarization, things are less variable than they used to be. Like, you can kind of talk things around in circles. It's hard to hold it all in your head at once. Like, it's like Florida, 43% in Florida, that seems too low. So like our lower bound for Florida, our 95% interval goes from like 46% for Biden to something else. I could see Biden getting 46% in Florida, but not 43. So I don't know. I think maybe Nate's doing something not quite right in terms of state correlations. Like, maybe his states aren't correlated enough, and so then you're getting these wide uncertainties. I'm not quite sure exactly.
Cool. Thank you so much. The comment section was blowing up while you were talking. That was a lot of fun for everyone. Thank you once again for giving us an outstanding talk, and we look forward to next year. You're already booked, by the way.
Okay, well, thanks for the opportunity to visit people I just wouldn't otherwise reach, who aren't students and are diverse people in so many ways. So thank you, Jared, for organizing this, and I'll see you later.
Absolutely. Thank you. All right, everyone. With that, we have our first afternoon break. Let's be back here. It'll be a little bit shorter because we had a little extra fun time with Andrew. Everyone will be back in the seats at 2:35. I'm going to go get a refill, and everyone will see you soon. Have a good one.